All right, good morning, everybody. My name is Patrick Schuff, as Matt already introduced me. So just to let you guys know, if you guys aren't familiar with what a production engineer is, a production engineer, you can kind of think of it like a SRE, so a site reliability engineer. So a production engineer is a role at Facebook where we kind of consider ourselves hybrid software/systems engineers. So in general, we do write a lot of code, but we tend to focus more on reliability, monitoring, and automation, and automating a lot of things to make sure our infrastructure is stable with code. So today we're going to talk about load balancing. We've built out a load balancing infrastructure. We'll talk about numbers in just a little bit. But I'm going to talk about load balancing by example. So we're going to start with assuming one single server served all of Facebook, so the entirety of Facebook. Every request comes in. And we're going to slowly build up, one by one, layer by layer, each of our load balancing infrastructure pieces so that we get to the point where we have a multi-data center, multi-continent load balancing infrastructure to serve all of the requests. A couple of points I want to make here is we use a lot of open source software. So almost all the pieces in this talk are going to be open source. There is going to be some custom stuff, Facebook specific to our environment, that aren't necessarily open source, but all of this stuff is easily done in open source, and I will talk about all of those different projects as well. And lastly, my goal for this talk is for you guys to think about the patterns that we use. Doing what we do for load balancing might not make sense for everybody, but kind of looking at the patterns and how we evolve our infrastructure and applying it to some of the things that you guys are building. So when people ask me what does a traffic engineer at Facebook do, this is the image that comes to mind. So this is a visualization showing all the people on Facebook and all their connections to all the other people on Facebook. Our job is to make sure that no matter where you are in the world, when you open up Facebook app on your phone or you type facebook.com into a web browser, that you connect to our servers as fast and secure as possible. So our job is to make sure that we're able to connect the world. That is the mission of Facebook, is to make the world more open and connected. So just to kind of quickly go over the agenda for today, we'll talk about the different types of requests that kind of make up Facebook. And specifically, we'll talk about dynamic requests. Then we'll dive into the actual protocol level and talk about how we do load balancing at the layer 4, layer 7, and layer 3 in the OSI model. Next, we'll talk about how we deploy servers around the world in internet exchanges and co-location facilities to reduce latency, and how just by having servers in region of the people who are using Facebook, it dramatically increases the performance. Lastly, we'll talk about DNS load balancing. We'll talk about how we determine where you are in the world, geographically and usually network-wise, and we'll talk about how we do DNS-based load balancing. And lastly, I'll open it up for Q&A, and you guys can ask any questions about load balancing, Facebook, production engineering, anything at all. So let's dive quickly and talk about some numbers real fast. So these are company-wide numbers. Every month, in the month of September, 1.79 billion people used Facebook. And on average over that month, 1.18 billion people used Facebook as well. So these numbers are really cool, and these are Facebook numbers, but I think about these in terms of a traffic engineer's perspective. So that means every day, assuming there's only one TCP connection per device, and this is, I think you guys all know this is probably very improbable, that means we at least have to terminate 1.18 billion TCP connections every single day and serve requests from those. And also, the really important, interesting thing is 1.09 billion are on mobile devices. So we have to think about people who are using high-speed, LTE or landline cable modems. But we also have to think about people using networks like 2G and 3G and all these different networking environments, and we need to make sure that we optimize those things. And lastly, I think it's really interesting that over 84.9% of people who use Facebook are outside of North America. So this, most of our data centers are in North America, and I'll talk about these in a little bit. But that also introduces a lot of challenges, and we'll talk about how we tackle those in a little bit. So from a traffic engineer's perspective, we can kind of generalize Facebook into two different categories. So the first is dynamic requests. And we can think of a dynamic request as anything, any request that is sent to our servers that can change over time. For example, your newsfeed. Throughout the day, you're going to receive different things in your newsfeed. So that will change over the day, and that's going to hit a web server. Secondly, anything that mutates state on the server is a dynamic request. For example, liking something, sending a message, that is also a dynamic request. On the other side of things is our static requests. So these are any requests that are going to be sent to our servers that are very, very unlikely to change. And these are very easily cacheable, photos, videos, et cetera. So the combination of these make us, we have a lot of people who use Facebook, and we send a lot of bits out to the network. So we are this means we send out terabits of egress to the internet per second. So egress is defined as the ones and zeros, all the bits leaving our routers, leaving the Facebook network. And today we're just going to focus primarily on dynamic requests. So these are any requests that are going to hit a web server. So just to kind of, one more time, just to kind of explain what we're talking about today, we're going to talk about the connections and load balancing, all the connections between the clients, the web browsers and the phones that are using Facebook and hitting an HHVM server. So HHVM is our hip-hop virtual machine. This is the web server. It's an open source web server that runs all of our PHP and hack code. So we're talking about the load balancers to get to those servers. We're not talking about any of the interesting load balancing we do inside the data center. So every time you fetch your newsfeed, hundreds of requests are going to a bunch of other services. Those are out of scope for this talk. So again, we need to make sure, we need to determine where you are in the world, and we need to connect you to these servers as fast as possible. So one of the primary metrics that the traffic team cares about is, again, egress. So this is a weekly view of our egress cycle. You can see every day that the top line there, it follows this really interesting curve. And and you can see there are two lines there. Most of the time when we look at egress, we look at week over week. So we look at egress today versus the egress the week before. And one of the really interesting things I learned, or I found when I joined Facebook is I was really surprised by how much these curves actually follow each other. So just any given week over week, the curves almost follow each other. They follow each other very well. And you can see the bottom line there, that's ingress. So these are the bits coming into our network. So all the requests, video uploads, et cetera. And as you can see, we send a lot more bits out of our network than we actually take in. So to break this down into a 24-hour period, we look at one day, this follows a diurnal egress cycle. And a diurnal is just a fancy way of saying any cycle that follows the sun or repeats itself every 24 hours. So as we can see here, our peak, so this is the peak egress. The peak ones and zeros leaving our router happens around 9 to 10 a.m. every day. And then you can see there's a trough there, and then there's another peak in the evening. And these are all Pacific time on this slide. But if we actually break it down even further, this is just the sum of all the time zones in the world. So we can break it down by region. We can look at EMEA, Europe, Asia, APAC. We can kind of see this, and this is just the sum of all the time zones in the world. So cool. So moving on, before we get into all the nitty-gritty, I want to do a quick review of TCP/IP. So here's a table showing the OSI model, the Open Systems Interconnection model. So this shows basically the model that was developed, I believe, in the late 70s, early 80s, to help standardize the communication between different devices. So, over time, we've kind of standardized on a lot of protocols, specific, internet protocols, specifically IP. So, layer 3 is the internet protocol. These are the packets that all of our routers are, routing between each other. Layer 4, we're going to talk specifically today about TCP, so transmission control protocol, keeping a connection and sending data through that, making it reliable and consistent. And then lastly, we'll talk about layer 7 load balancing. So this is, for the purposes of this talk, we'll just focus on HTTP because it's plain text. But with that said, we do use a lot of HTTP too, and it would be hard to put binary things up here on the slides. So we'll focus specifically on HTTP for today. So again, looking at each of these protocols, the IP, this is an IPv6 header, so a lot of fancy stuff in there. For the purpose of today, all we really care about is the source address and destination address that these packets are originating and going to. So for the TCP, again, there's a lot of information in here. What we really primarily care about for the purpose of this talk is the source port and the destination port. And then lastly, our HTTP request. So this is layer 7, and again, it's just a simple GET request. So putting it all together, and this is how the OSI model works, is you have your application layer request. So you have layer 7, and then that is encapsulated in a layer 4 TCP segment. And then that is encapsulated in a layer 3 IP packet. So this is, for the rest of the talk, this is how I'll be talking about, this is how I'll be visualizing a simple request. So diving into serving dynamic requests. So we're going to start assuming that one single HHVM web server is serving traffic for 0.09 billion people that are using Facebook every day. So you have your client. It's going to make a DNS request. So it sends a quad A request for www.facebook.com. And it's going to get a request back for that single web server serving everybody. So then that client needs to establish a TCP connection, and it's going to establish an SSL. It's going to be HTTPS, so it's going to TCP, then the SSL handshake. And then finally, it's going to return that request. So this works in a very small environment, but we need a lot more HHVM web servers to support all of Facebook. So how do we solve this? Is we add another load balancer in front of it. So assuming the same setup, we send the DNS request from the device, and then we add this L7 load balancer, and we call it ProxyGen as our internal name for it. So ProxyGen's job is to terminate that TCP and SSL connection, and then it takes that L7 request and it proxies it back to one of the HHVM servers. And this is very easily, ProxyGen, we do have part of the libraries open source on GitHub, so you can check those out. But ProxyGen can easily be replaced with Nginx, Hot Proxy, Apache Traffic Server. There's probably a plethora of other things that can be in that place. So cool. So now we've terminated all the TCP and SSL connections on this one L7 ProxyGen server, and we have a lot more HHVMs behind it. But we still need a lot more RPS. We still need a lot more HHVM servers, and that ProxyGen server is a single point of failure. So how do we solve adding more ProxyGens? Is we add another load balancer in front of it. So this is where we introduce our L4 load balancer. So this is a TCP load balancer, and we use the open source kernel module called IPVS, IP Virtual Server. So the request comes into the L4 load balancer, and the way this works, and we're going to talk about this in a little bit more detail in a little bit, but that packet comes in, and then it gets consistently hashed to one of those L7 load balancers. And that's really important because the L7 load balancers are what are keeping the TCP connection. We're actually establishing the connection with TCP. So it's really important that we keep that connection with the L7 load balancer. Otherwise, we break that TCP connection. So we'll talk about that a little bit more in a little bit. So this is great. We can add a lot more L7 load balancers to terminate TCP and SSL and proxy that HTTP request. We can add many, many more HHVM servers behind it. But we're still, we still have a single point of failure in this single L4 load balancer, and it can't handle all the traffic coming into it. So how do we solve this? We add another load balancer in front of it. So this is where we're actually using the routers to do load balancing. We'll talk again a little bit. We'll talk about this in more detail. But so the way this works is the request comes into the router, and then the routers use a load balancing feature called ECMP. So this is equal cost multipathing. So what happens is that request comes into the router. It gets consistently hashed to one of the the IPVS layer 4 load balancers. That request gets consistently hashed to the L7 load balancers, keeping that TCP connection alive. So we're really relying a lot on the consistent hashing of all these things. And we'll talk about what happens if the consistent hashing doesn't happen and how we can still preserve those TCP connections a little bit later. So this is our units of, this is what we consider a cluster. So this is basically what we would consider a front-end cluster. So we have, potentially tens of L4 load balancers here. We have potentially hundreds of L7 load balancers, and then we can have many thousands, up to tens of thousands of HHVM servers behind it. So this is basically our unit of front-end capacity at Facebook. There's a lot of servers there. So cool. So this is great. So now we have 10,000 HHVM servers, but this still isn't nearly enough to actually serve all of the traffic at Facebook, and it's a single point of failure. A hurricane can come in at any time and take out one of our data centers on the East Coast. So we need to add redundancy. So what do? Is we add another cluster. So we can add, we can start adding on all of these front-end clusters to help, increase the capacity. What's important to note is we do have a lot of different cluster types. We have database clusters and kind of generic clusters, but for the purpose of this talk, we'll just focus on the front-end clusters. So this is great. So we have multiple clusters, and multiple clusters are what we consider a data center. So a data center just consists of multiple of these front-end clusters. So this is great, and I kind of jumped ahead, but again, a hurricane could wipe out any of our data centers at any time, or any other catastrophe. So we need to have diversity in our data centers. So how do we add more capacity and diversity? We add another data center. So this is where this is how we build up the capacity to actually serve all of the requests coming into Facebook. Cool. One important thing I want to stress is I've kind of shown this on a very top-down approach where the requests are coming into servers and they look like they're directly connected to the other servers. We actually use a really flat infrastructure. So these clusters are filled with all of the exact same servers, and all of these, these different load balancers are running on this commodity x86 server. So we don't have special servers to do all of these different functions. We have, it's kind of like a Kubernetes Docker type deployment system that allows us to schedule these jobs out to systems. And if that server dies, it will get scheduled somewhere else. So it'll take one of these HHVM servers out of rotation, and it will just put that layer 4 load balancer on there. So it makes it really nice and very easy to scale up and scale down, based on hardware generation or capacity needs. So here are our different data center locations. We have one international outside of the U.S. in Luleå, Sweden. We are building another one in Ireland. So we are building out as many data centers as we possibly can, and we're adding more all the time. So as people continue to use Facebook, we are increasing capacity to in this way. We're building data centers and we're putting these clusters there so that we can serve all of these requests. So now let's dig into the actual protocols a little bit. So breaking it down, again, here's the OSI model, and here's where each of those load balancing infrastructure pieces fit within that model. So we can see at layer 3, this is where we use the router. So these are switching packets at line rate and using ECMP, equal cost multipathing, to load balance these IP packets across all of the L4 load balancers using IPVS. Layer 4-wise, we use IPVS, and this is taking the requests and consistently hashing them all to the L7 load balancers, which are layer 7 using ProxyGen. So the way this actually works in practice is we have the L4 load balancers. And again, I mentioned that these things are scheduled out to servers. So the way this works is we schedule this out to one of the servers. It loads that IPVS kernel module. And we have some Python that basically sets up the routing for the IPVS perspective. And then we spin up an exabgp job on that server using exabgp is an open source Python BGP daemon. And then what that does is it establishes a BGP connection to the top of rack, which gets propagated throughout our infrastructure. So BGP, if you guys aren't familiar, is the Border Gateway Protocol. It's a very common internet protocol for routers to talk to each other and announce what routes do you have. So in this case, we have regular servers talking to these routers saying, I have this IP address, I have this VIP for this web server. So the L4 load balancers will peer with the top of rack. It will announce a /32 for IPv4 or a /64 for IPv6, and then that traffic will start flowing into that L4 load balancer. So that's how we determine reachability between the router and the layer 4 load balancers. So moving on between the L4 load balancers and the L7 load balancers, it's very common way to configure load balancers is you can think of it as you have these pool members behind it. So we use the exact same model. So the L4 load balancers have a pool of hosts that it knows can handle the requests that it has. And the way we do this is we've built our own service discovery frameworks on top of Zookeeper. So Zookeeper handles all of it basically keeps a map of all of these L7 load balancers, which are consumed by the IPv4, the L4 load balancers. So the request comes into the L4 load balancers. It looks at basically all the pool members behind it. It does a consistent hash on that request, and then it gets sent to the L7 load balancers. So one thing I kind of glossed over, which is very important, is how the consistent hashing function works. So when that request comes into the L4 load balancer, it does a consistent hash on the 4-tuple of that socket or of that connection. So that means it does a hash on the source IP, source port, destination IP, destination port. So it takes that 4-tuple, it does a consistent hash on it, and that determines which L7 load balancers that gets sent to. It might make more sense in this next slide. So we're going to walk through an example of what this actually looks like when the request is coming in. So we have a client, we have a phone, using Facebook. The request comes in. We'll just kind of skip the router part for now. We'll just assume that it gets sent to the L4 load balancer. So the request comes in. It does a consistent hash on the 4-tuple, and then it gets consistently hashed to one of these L7 load balancers. So one really important feature of the L4 load balancers is it keeps a state table, and this is local to the server, so this is all done in the kernel. So it keeps the state table of where it actually sent these connections, and it'll make sense why this is important in just a minute. So that request comes in. Every time it sees that L4 load balancer, it does a lookup in its hash table, its local hash table, and then it will say, oh yeah, I sent it to server A. So cool. So another request comes in to one of the other L4 load balancers, from a browser, and then it gets sent to D. So everything is just consistently hashed. So what happens if we actually lose one of these L4 load balancers? So this client A has a connection with ProxyGen server A. So it's as a TCP connection established. So assuming that L4 load balancer goes away, those requests are now going to go to one of the other L4 load balancers, whichever the router decides to send it to. So the important thing here is since all of these L4 load balancers are using the exact same consistent hash, and since they have the exact same pool members behind it, that request will get sent back to that same server. So this is how we preserve the TCP connection when we have some fluctuations inside one of our layers of load balancing. So let's look at what happens if we lose one of our L7 load balancers. So the A client had a connection with the A ProxyGen. That server went away. So we have to break that TCP connection. So the request comes in, and then it gets consistently hashed to another server. And it just happens to be B. It could be any of these L7 load balancers. So again, it sees where this connection is going, and it remembers that it gets sent to B. So it keeps that in its local state table. So what happens when this ProxyGen, this L7 load balancer comes back? So the requests are going to keep coming in, but since the L4 load balancer, the first thing it does is look in its local state table of where that connection went to, where it was sending it to. It actually will continue to go with B, so we don't break any TCP connections here as well. So here's the example. That request is going to come in. It's going to continue to send to to the B L7 load balancer. So one thing I also glossed over in a lot of this is we use a load balancing technique called DSR. So this is direct server return. So that means these requests come into the L4 load balancer. They get sent to the L7 load balancer. The L7 load balancer will proxy that request, get the response, and then the response to the client actually leaves directly from that L7 load balancer and cuts the L4 load balancer out of the loop on the egress path. So the way this works is, we know how these requests work from a protocol level. The way this works is the L4 load balancer takes the request. Again, it does a consistent hash, and then it puts a packet around it. So it actually wraps that original request in another IP packet. So this is called IP and IP encapsulation. So looking at an example of how this works, the request comes in, it comes to the L4 load balancer, consistently hashes and determines which L7 load balancer it should go to. Then it puts an IP packet on top of it. So with the destination address being the IP address on ETH0 of the L7 load balancer. So the L7 load balancer looks at that request, or it looks at that packet, it says, yes, I do have this IP address, and then it looks at the next protocol in the IP header, and it sees that it's just another IP packet. So what happens is it just decapsulates that top packet, and then it drops that IP packet back on the networking stack on the Linux server. And then it says, OK, yeah, I do actually have this, because the L7 load balancer is listening on whatever VIP we are sending these on its loopback interface. So it's not listening to these on ETH0, because that would just cause networking weirdness in our network. But it's just listening on that public VIP on its loopback address. So this is how we can have these, these non-internet-facing servers actually serving these requests. So the L7 load balancer sees the original request, processes it, and then sends that directly back to the user. So that's the kind of in a nutshell how DSR, direct server return, works. So moving on, oops, sorry.
Why is the encapsulation needed if you've got the IP on?
What, the question is, why is the encapsulation needed?
You've got the IP on the loopback interface.
Because we wouldn't know where to send it. I mean, we have to send it to one of the L7 load balancers.
You can do that without rewriting.
Yeah. Yep. So yeah. So I guess another fact about there's also layer 2 DSR, which I probably shouldn't even mention, but our network topology at Facebook is entirely layer 3. So we do layer 3 routing from all of our top of racks. So this is why we do layer 3 DSR instead of layer 2. So layer 2 is an exercise for you guys to look up later. So cool. Any other questions before we? Cool. All right. So let's talk about how we deploy servers around the world to help reduce latency. Back in 2011, the traffic team did some studies to figure out around the world how good or bad is the experience, how do people experience Facebook. So, and they were doing this based on networking, so looking at the round trip time. So as you can see, in North America, we only had 3 data centers at the time, all located in the US. So in North America, they had a pretty good experience. Everybody was pretty close to the web servers that were serving their requests. But the further you got away from North America, the worse the experience got. So the traffic team went on a mission to figure out how we can solve this problem and how we can, even though we do only have data centers in the United States, how can we still improve the experience for everybody on Facebook? So let's look at an example of a phone in Seoul, South Korea, connecting to one of our data centers in Oregon. So we're going to assume for the purpose of this, and it's approximately true, that the time it takes for a packet to travel across the ocean is about 75 milliseconds. So, which isn't that long, but we'll see why it actually is pretty long. So just to establish, we'll look at this from the protocol level. So just to establish TCP, we all know, you do the SYN, SYNAC, ACK. So that is establishing the TCP connection. It's a 3-way handshake, which requires 1 round trip across the ocean. So this takes 150 milliseconds. Next, we have to establish SSL. So this is a 4-way handshake, and this requires 2 full round trips across the ocean just to establish TCP and SSL connection. At which point, we finally get to do the real work that we wanted to do this entire time, is send that HTTP request, which requires 1 more round trip. And just for a single request, it takes 600 milliseconds. So now let's look at what happens if we deploy servers in the region where that client is in to establish TCP and SSL. So let's see how this improves things. So we'll assume that we have a POP in Narita, Japan, and it's about 15 milliseconds from where that client is connecting from. So let's look at this again. So we establish TCP and SSL. Just by putting that POP much closer, we can establish TCP and SSL in only 90 milliseconds, which took 450 milliseconds before. And then we can actually send the 1 request that needs to travel across the ocean to an actual web server to be served. So all this is done in 240 milliseconds. So just by deploying servers and terminating TCP and SSL closer to users, we've improved our round trip time by over 50%. So there's a really big performance win by actually doing these things as close as possible and only offloading the work that's really important back to the expensive oceanic links. So we have many different edge pops around the world, and we're trying to deploy as many as possible. But it's important to note that all of your TCP connections are going to be terminated at one of these POPs, one of these edge locations, and your request will be sent back to one of our data centers to actually be processed. So you might be asking, what does the load balancing look like in one of these POPs? So we've already seen what it looks like in one of our front-end clusters. Fortunately, it's the exact same stack. So we have the request coming into one of our routers. It gets ECMP'd to an L4 load balancer, and it gets terminated by an L7 load balancer. The only difference between this and our data centers is we don't have any of the HHVM servers. So all these layer 7 load balancers are doing is terminating those requests and then proxying them back to our data centers, which is running the stack that we've already seen. So the L7 load balancers and all of our POPs have pre-established HTTPS connections back to all of these. So all it's doing, taking the request, forwarding it onto the data center, it's getting that response back, and then sending that back to the client. Cool. Any questions? OK. So lastly, we'll talk about our DNS load balancer and basically our world mapping system called Cartographer. So again, we have all of these different edge POP locations, but now we need to make the decision of how do we know where to send people who are using Facebook? We need to basically decide, at DNS request time, where are we going to send you to all of these POPs? And another important thing to note is none of these POPs have enough capacity to serve an entire region. So every POP is constrained in one way or another. So we need to be really smart and not overload POPs and overload any of the finite resources that we have in each of these locations. So some of the different considerations of where to send these connections. The first one is closest edge to the client. And what's really interesting about the internet, and if you can figure this out if you do trace routes, is the internet is not, just because you're physically close to something doesn't mean your network close to something. The internet's really clowny in a lot of ways, and your packets get routed all over. It really depends on the ISPs, the backbone infrastructure, how BGP is laid out. So just because you're physically close doesn't mean you're actually going to be close. So that's a really important distinction to make. So the way we do this is we measure how close you are to our POPs based on network. So we'll talk about Sonar in just a minute. Again, capacity is really important. We have these in internet exchanges. We have links on our routers that only have finite capacity. We have servers that have finite CPU and memory capacity. So there's a lot of different considerations that we need to think about when we start allocating new connections to one of these POPs. Thirdly, we have health. So the POP could be completely healthy, but somebody cut a cable across the ocean, and we have limited connectivity to it. So or we could have just lost a link. We could have lost a router. So and dropping a lot of packets. So health is also another really important thing to think about outside of kind of the capacity constraints. And lastly, one thing we can fall back on if we don't have enough information is we can fall back on geodata. So we can assume that the internet's not that clowny if we don't have enough data, and we can try to allocate you to the closest place. So the way we do this measurement is with a system called Sonar. So Sonar is a system that basically every 40,000 or so profile pictures that get served to Facebook to clients, we send to a suboptimal POP location. So just because you're here, you might get sent, instead of going to IAD or whatever the closest POP is, you might get sent to Seattle or something. So by doing this, this allows us to do these sampling of measurements to all the different locations around the world. And even though we're only doing one in approximately 40,000, this ends up being a lot of data at the end of the day. So we have a pretty good idea of, based on most of the IP blocks or network prefixes around the world, how close you are to all of our different POPs. So Cartographer is the system that takes all of this data and makes these real-time decisions on where to allocate each DNS request or each CDN request. So it takes all of these different inputs, and it used to be written in Python, but it did end up getting rewritten in C++ for performance reasons. But it creates this map of the world, and this map gets rotated approximately every 1 to 2 minutes. And then we use a torrent infrastructure to torrent these DNS maps to thousands of servers actually running DNS. So this map is updated quite frequently in response to different network anomalies or different capacity constraints. So this is just kind of another visualization of the different ISPs. So that request is going to come in. And then we have, based on the different resolvers, we will allocate all the different clients to the different POPs. So looking at Cartographer in action, so this green line here is you can see the capacity limit there. It's kind of hard to see. It's kind of light green. This is where Cartographer thinks the capacity should be. You can see that orangish red line is what it would actually be if we didn't have Cartographer. So this is the actual load on this specific POP, assuming we didn't have anything keeping the capacity where it needed to be. And you can see that kind of jaggedy little line there, the green one. That's where Cartographer actually kept it right where it needed to be. So Cartographer's job is to take all of these different inputs and keep capacity and keep all the connections that are happening to these POPs as close as possible to those utilization limits. So this is what it looks like on a regional level. You can think of this as having multiple POPs in Europe. And basically, at trough there, everybody's sleeping and not really using Facebook. Everybody starts waking up, and you can see all of them hit their capacity limits. So you can see Cartographer's doing a really good job of a POP hitting its limit, and then it will start shedding that traffic to the next best location. And then it will keep doing that until all the traffic is served. And then this is what it looks like from a global perspective. So you can see many different POPs. And as we saw early on in the slides, every region has a different egress pattern. We have time zones in the world. So, every POP cannot handle all the load. Otherwise, the curve would look like this. So, Cartographer's job is to make sure every single day that every request is being allocated in the most optimal location. So cool. Again, I mentioned we use a lot of open source. All of this can be built with open source software. So, Proxygen HHVM. We use TinyDNS for our DNS server. A lot of the load balancing infrastructure, at least the automation pieces, are written in Python. I do encourage you guys all to check out our GitHub page. We do have a lot of different open source projects on there. And lastly, I just want to thank everybody on behalf of the traffic team at Facebook. Thanks.
Hi.
Hi.
Thanks for a great talk.
Yeah, thanks.
So I'm curious, the whole load balancing infrastructure is quite complex. It follows this sort of traditional pattern of having these middle boxes where you have your L4, your L7, and so on and so on. Mm-hmm. And I wondered, because you're scaling different kinds of traffic in different ways, you've got your CDN infrastructure,
yeah.
Why didn't you go for a simpler system where you use more of a CDN kind of scaling for the whole stack, using some kind of directory service to mediate a direct point-to-point connection to the servers, rather than going through these points of failure in between that add latency?
I don't quite understand what you mean by a director for point-to-point service.
Just like, say, DNS connection, where you have I guess what in the old days you would call dynamic DNS, mm-hmm. where you're rewriting your directory service, connecting. You're asking for Facebook service, and you connect to a load balanced directory service, but that's quite easy to scale. No data being transferred. And then that points you directly to a server instead of pointing you to a load balancer, to another load balancer, to another load balancer.
Sure, I see. So you're saying, why didn't you use DNS as a service discovery type thing and do the load balancing on the client side?
Yes, exactly, but not necessarily DNS, something more modern, because you're using Zookeeper already and updating that pretty quickly. So I figure some modernized DNS-like thing could do it.
Yeah, I think this was probably an architectural decision to not build the load balancing into the clients. So when you think about 1.0 or 1.79 billion people using Facebook, the amount of clients that are using Facebook is enormous, and people don't always update, their software. And we have a lot of different. We even have people using Facebook on feature phones. So like these really, pretty basic phones compared to what we're used to. So having the decision be on the client side, and I think is just architecturally, we didn't want to have to deal with that. I think it's a lot simpler just to do this on the server side and do it based on, this talk is primarily about DNS-based load balancing. Had I had more time, I would have talked more about CDN. And one of the things we do with CDN, it's actually a lot better targeting, because when you generate your newsfeed, we know all of the photos and videos that are going to be in your newsfeed, and we actually send you URLs exactly where we want you to be sent to. So it's actually a lot better targeting, and had I had more time, I would have included that in the talk. So we actually do have pretty good targeting, because in that case, when we have generating your newsfeed, we already know your client IP address. We don't have to aggregate you to a DNS resolver. So I guess the long story short is it was an architectural decision to move it to the server, and also that we do have a lot better ways of targeting non-dynamic requests as well.
Thanks so much. Great talk.
Yeah, thank you.
I'm Zach from Res1, and my question is specifically around encryption. So you mentioned you guys saved, I think it was about 400 milliseconds on every connection attempt by terminating SSL closer.
Yep.
Do you then encrypt between your POPs and your data center? Is that already an encrypted tunnel that's up? How does that all work?
Absolutely, yeah. So we're using HTTPS between, absolutely, yeah. Everything going over our backbone is encrypted, for sure. So, but we have a pre-established pool of connections, already established HTTPS connections, so that we can just fire those off. So we don't need to pay the penalty of TCP for all the things backhaul going to our data centers. And another thing that I said that a TLS connection is a four-way. There are ways to reduce that. So we use TLS ticket keys is a way to do, I think, a one round trip, assuming you've already touched this server within the last whatever time period. We can use TLS ticket keys for session resumption, and there's also server-side session resumption for TLS. So we do a lot of things to also reduce that two-way round trip as well.
Awesome, thank
Cool.
you.
Yep.
Hi. How do you come up with the limits of the capacity for each POP, and how do you keep them current? Like, how do you know that really is what the POP's capacity is, and you can't go higher?
Absolutely. So just because you have a rack of servers doesn't mean that every different region where you put that in is going to have the exact same capacity. So when you deploy servers in I would say a region that is very heavy video, it's actually a lot cheaper on the CPU to deliver video. Like, you're sending a lot more bits out of these 10 or 40 gig interfaces, but it's a lot less CPU consumption. But when you go into a country where they consume a lot more photos and videos, there's a lot different CPU patterns. And to answer your question, it's all cartographer's job. Cartographer's job is to say, based on this RPS load, how much NIC utilization, how much CPU utilization are we actually using? And it also monitors all of the links between the internet exchange and the ISPs. So cartographer's job is to keep this right at the limit.
So you're saying cartographer is getting real-time data from each POP?
Yeah, absolutely.
On
Cartographer,
how healthy it is.
Cartographer BGP peers with all of our routers, so it knows all the routes to the internet. It real time will go and query all of our ProxyGen servers. So it queries like how much requests they're doing. It queries CPU utilization. So yeah, it's doing this all in real time and aggregating a map of the world.
This question about location of a POP. So how do you decide the location? Because in the initial couple of slides, I saw that the Indian subcontinent had a disproportionately large number of users, but there is no POP there.
Yeah.
So is it only technical, or?
No, absolutely not. If we could put a POP everywhere, we would put a POP in everywhere where there are people. But there's a lot of considerations when we put POPs. You have to think about space and power. it costs a lot different. There's a lot different cost structures in North America and Europe compared to Asia. So you have to think about space and power. You have to think about internet connectivity. So in some places in the world, internet connectivity is really expensive, in comparison to other regions. And then there's a whole bunch of policy and types of things that also go into these decisions as well. But yeah, if we could put a POP everywhere, we definitely would.
Thank you.
Yep. And lastly, I just want to say we have a booth out there, and I'll be there, today and tomorrow with several other Facebook engineers, and we'll be happy to talk with you guys if you have any more questions. Cool. Thanks.
Patrick, thank you so much.